there is no system. I will need later. I will need to refocus on this. I don't know. Maybe no one needs it, but maybe by the time of some homeworks, you will wish to watch the recording. Maybe not. But, we'll try to keep this. So, with action and angular momentum. Why? Who needs that? Any ideas? And before we go to details, probably we'll do a little refresher of last meeting. But what did we do last time before we start?
Talked about waves.
Huh?
Talked about waves.
Yes, we derived the wave equation and second derivative over space equals second derivative over time, right? And then there were some movies with music. What were they about? To your best memory.
Movement, electrons,
Or
and like something is like wrapping around
something circular.
centers.
So we will very soon come to a very organized and like scheduled set of equations and material. Right now we are more philosophically discussing stuff. But about by the time of beginning of World War I, the science was really powerful. It was explaining many things and helping to engineer new devices all the time. But there were a couple of things that were keeping surprising brains. And one of the things is that if we believe that atom is positive nuclei with negative electron, and electron is attracted by electrostatics on one hand. So centri, I always mix this word, one centrifugal and another centripetal. And because of kinetic energy, it wants to go away, right? And then it holds together. But if one accepts this concept and believes in classic electricity, classic dynamics, then the electron should slow down continuously, slower and slower and slower, emit infrared at any continuous range of frequencies, and finally fall down in the ion. So atoms should not exist as they are. They all should collapse. And they should emit the continuous spectrum. But in all experiments, whoever practiced the spectrophotometry? Okay, so how spectral dependence of intensity as function of frequency? Just roughly, just show something in the data. But there are peaks, right? And peaks have width, and sometimes there are more than one. And if we are looking at spectral atoms, then peaks are very sharp and narrow, which goes very against the classical picture. So something was wrong. I always try to skip this discussion because it seems that you all know the answer, right? Why electron doesn't fall on nuclei and why atomic spectra are linear rather than continuous. You do. Maybe we need to establish connections between this information in your heads, but you were answering last time. So remember S, P, D, orbitals. So like there is S, P, D orbital. Is there like orbital in between? Or not for molecule without hybridization, but simple atom. Can it be like in between S and P? Oh, you know this, right? So by some reason in atoms, electrons take specific orbits and they cannot be in between these orbits, right? So there is something that, and if you look in d orbital, it looks like a little flower with petals. So number of petals is always discrete. So it's 0 for S, 2 for P, 4 for D, and 4 for F. Right? So number of these petals is discrete. Why? Do you remember anything by the way, approximately? It's fine if you don't remember, but it was if you would answer this question 110 years ago, you would win Nobel Prize in physics and chemistry. So it was a really big question. And the mathematical explanation came about 10 years earlier than philosophy. So it's really one of the cornerstones of modern science. So it deals with these standing waves we discussed last time. So the electron forms standing waves, and they are standing waves on the circular orbits. So the electron is a wave that goes along a specific trajectory and forms standing wave with a discrete number of maximum of minimum. Right? Simple. Who designed this model? Yes. So Bohr's model is this stuff. And we will briefly touch this model today, and then some of you will potentially select it for presentation at the very end of the semester. Then we will go to this more details. But for understanding or making connection between waves, atoms, or model, we need these two concepts: twist action and angular momentum. Okay. So twist action is needed to explain why electron prefers to go along a specific trajectory, although it can deviate, but there is some primary trajectory. And angular momentum is needed because for curvilinear motion, regular momentum is not applicable. If nothing goes straight, something is concerned. Twist action, I probably can even jump to last slide. If it tells you something, if you are comfortable with the last slide, you do not need anything else. So let me focus on the screen. So if these symbols seem, if you feel comfortable with them, you can just stand up and I will try to set up the narration that this yellow phrase about accumulation of phase will induce only positive emotion. So let me see if I'm intelligent enough to follow the answer. Maybe not. Oh, okay, yes. So last time we considered standing waves, which are created by superposition of running waves, right? And then we have spatial part and temporal part, and then there are nodal points where nothing is changing. And we practiced the derivatives and found that second derivative over space and time give the same thing for this wave function, so to say. And then the wave equation includes second derivative over space and time and philosophy. And then there was a little illustration about the ancient TV, right? So if the electron is going through a slit, then one intuitively expects sparks on the sensitive screen only on the straight line between source electrons and slit point. But in fact, there are signals in between, right? Because of the wave nature of the electron. If one looks on the double-slit keyword in Wikipedia, it will show that it's not just a signal in between, it will be fringes everywhere. And if you were taking classes or making experiments, something related to waves, highly likely you would see. And then you may have seen, if you were not living immediately, there were a couple of
Never gonna give you up, never gonna let you down, never gonna run around and desert you, never gonna make you cry, never gonna say goodbye.
We will go to details later. Right now, I do not want. I just, for some of you, I can make disclaimer: standing wave doesn't move, but real and imaginary part, since wave that corresponds to motion of electron is complex, real and imaginary part makes a motion. And the little, not proof, but demonstration that number of number of little points must be discrete. If it is not discrete, then the image will be not static. It will change in time and will be not solution, not stationary state. It will decompose with time. So we are looking on one-dimensional electron making on the linear trajectory, which is a big lie. It's, or scientifically, a big approximation. If you want to be polite and you want to say to someone that you're not quite telling the truth, and what you're telling is a big approximation. So if one assumes that it is one-dimensional wave along a trajectory, then a measure of angular motion is angular momentum. So it's a cross product of position of this thing that is rotating times momentum. And both position and momentum are changing with time if something is moving circularly, but this product stays constant if there is no external perturbation. And it is a very good quantity to do this if one is going to describe it. So what is in the second frame? We already discussed it, but you may give a right name. So absolute value of the angular momentum equals Planck constant times integer number. So it is a summary of Bohr theory. So the electron moves around nuclei is only specific, permitted, discrete values of angular momentum. And again, do not focus too much on it, because Bohr theory is a big approximation. It is only as a step towards developing more useful things. discrete values. So which 0 for S, 1 for P, 2 for D. So angular momentum is a measure of angular motion. Good. Same as, so it represents inertia. If there is no external perturbation, something is rotating with constant angular momentum. There is an interesting observation that the Planck constant has the same dimensionality as angular momentum. Of course, everything is set up. It was set up to have this dimensionality, but for us who are starting to look at it, it's an interesting observation. And if you divide angular momentum onto a Planck constant, which is like h, which there are h and h bar which differ by 2 pi. So if you divide it by h with bar, then the dimensionality of this fraction will be angle. And depending on the value of angular momentum in Bohr's atom, it will be like 2 pi times integer number. So how do we interpret it? So there is a circular motion. There is angular momentum divided by constant that gives angle on one hand. And on another hand, we have standing waves. We have waves that change its phase. It's very natural assumption, although there is no direct logic, but it is like a prompt, a hint. Can it be that angular momentum divided by Planck constant is an argument that comes inside the sine or cosine wave? Because dimensions cancel, we have angle in units of like 2 pi, and if n equals 0, it will be cosine of 0 will be constant everywhere, s orbital. If it will be 1, it will be 1 cosine function. If it is 2, it will be like more. So in radial system of coordinates, one can generate these patterns for SPD orbitals. On one hand. On another hand, there is some internal connection between this angular momentum and motion of electrons. So something, maybe this angular momentum somehow enters into equations. So what I'm telling right now is yet vague, but very soon we will come to more organized system of connected equations possibility. What's that? Huh? Exactly, yeah, perfect. So acceleration equals force divided by mass, right? So if we solve this equation, it is inertia. If there is no force, then no acceleration, and an object will move with constant velocity or constant momentum, right? Until it being hit by something that exerts force. And if one looks onto acceleration as second derivative of coordinate, then one can predict materialistically mostly anything in the world. Like if you do molecular dynamics of proteins, you just solve Newton's equation. But is there anything better than Newton's equation that answers the same question? Something which gives the same answers but is a little more advanced, more theoretical, and maybe more universal. Well, there is an answer. You see it, right? Here. And, so the wave equations are not
design of recent 100 years. They were developed at least 200 years ago, so about the time of Napoleon Wars. They were originally applied just to describe the string on a music instrument, because it also has some wavy motion. And objectively, a string or any wave, it consists of like a very large number of little chains, and each of which needs to be tracked down. So one needs special math to describe. On one hand. On the other hand, there were thinkers who were trying to design equations that can be equally applicable not only to linear motion but also to circular or to system of connected like objects. And this one gives answer to the same questions as Newton equation, but from a little different angle. Have you seen this name before this class? So what does it tell? Just vaguely, it's okay. So it is more mathematical. How to solve differential equations? Good.
Range points in space.
Oh, so it is about like satellites. Super. Yeah, that's great. So you know the name. It's a point when two like planets or Sun and Earth attract a satellite with equal strength, right? So he was a productive scientist, but there is the main contribution is that he designed equation that like Lagrange equation instead of Newton equation, and it appeals to what most of us like, doing nothing. Principle of least action. Maybe not for humans, but for objects that you describe. So they try to act less than possible. So we are going to connect several concepts, and we can describe them either by words or later by equations. So if you do have Newton's equation of motion, you start from equation of motion, and then your main answer that you generate is trajectory. Right? Please give a little sign if you do not feel comfortable with this verbal formula. By solving Newton's equation of motion, one generates trajectory. Right? Do not hesitate. It's not an exam. If you do not feel comfortable, you better tell me. I'll try to describe it differently. So the goal of like basic mechanics that you may have studied already in physics is to predict how an object will move with time. So position as function of time, which is called trajectory. And this trajectory is typically generated by solving equation of motion. Now we are not going to derive things. We are going just to follow logic in the opposite direction. Suppose that we have equation of motion and look which equations may generate this solution. Same as we did for wave equation. I bet you are not yet in the mood to go to the blackboard, but if you want to convince the opposite, just let me know. Those will be simple things, so simple that I can do them myself. As soon as we come to something more complicated, please be prepared. I will be calling everyone to the board to do it. So trajectory means you have position as function of time, right? So what is, and then one can also immediately get the velocity or one can multiply the mass and then over this momentum function. Now, kinetic energy. Why it is needed? Well, because sometimes if an object decelerates, then kinetic energy decreases, but it gives energy into some potential, and one needs to track them down. So what is kinetic energy?
Is that a divide symbol?
It is equal symbol.
That's an equal symbol. Yes.
I am worst calligrapher in the world, especially with this touch screen. So what is kinetic energy?
1/2.
1/2
And
mv squared. Yeah, which will be like 1/2 m dt x of t squared, or 1/2 p squared over m. So if we do know trajectory, we immediately know kinetic energy, how it changes in this time, right? It's not a big deal. If we know trajectory, we can express kinetic energy at each point. What is potential energy? You can answer that question is posed in the incorrect way, and I decline to answer. Because potential energy is very different for each problem, for each system, right? So you need to request more precise questions, like potential energy of what? Let's say potential energy of mass on a spring. But I can write a question myself. Just give me, please, a little idea of what is potential energy. Huh? Yes, stored energy.
so it hasn't become kinetic yet.
Yes, something that can be released, conserved. Yeah, very good. The simplest potential energy that we can harness.
Absolute energy minus kinetic energy.
Super. And how can I demonstrate what is potential energy?
Something.
Huh?
Is it over?
Or just lift a little. So we are in a gravitational field. And as soon as anything is lifted, it has potential energy. If I drop it, it will accelerate. And if it is like mass on a spring, it will be something like spring constant x squared over 2, right? Good. So total energy. It's not a truth question, it's truth question. So Hamiltonian means total energy. So since we know kinetic and we know potential, what is total energy?
Kinetic energy plus potential.
Yes. So you can introduce like more the symbol kinetic K, potential U, the total will be kinetic plus potential. So if we do know trajectory, then we can express total energy at each point of time, right? And we expect that total energy is conserved, right? Conservation of energy. So Hamiltonian is because of Newton. He is based on this total energy of the. Suppose that your personality dictates you to argue with everyone. There are people who want to. How can you speak about similar objects but design a little bit different expression? What can be easily changed in here? Just give some arbitrary, crazy ideas.
Kinetic minus
Exactly.
negative.
Did you knew before, or it was a new design?
I thought of that.
Okay, so the Lagrangian will be kinetic minus potential. And there is a very interesting observation. So right now we only like superficially observe these equations and discuss them. We are not going to derive. But there is a mathematical construction. This Lagrangian function depends on time. If one integrates this Lagrangian function from initial to final moment of trajectory, this variable is called action, and so I'm going to tell something verbally and with hand waving. Suppose that you already have solution, you have the trajectory of some natural object. It doesn't need to be a lot. It can be a chair falling down, or maybe a satellite revolving around the planet, or like a mechanism where several things, several masses interact with each other. So suppose we have trajectory of an object, and then we have a correct right trajectory, and we compute this action for a right trajectory. Then we go crazy and draw a trajectory that is not right. It deviates. And compute this action for a wrong trajectory. So the action for a wrong trajectory will be always bigger than the action for the right trajectory. So a way to find a right trajectory can be as follows. Draw arbitrary, like 1,000 arbitrary trajectories, find action for each of them, and sort them according to the value of action. The one that will give least action will be the closest to the what we observe in experiment. And this is called least action principle. Just generate arbitrary trajectory, find action, and compare it with other actions. Or modify trajectory slightly until you can decrease the value of action. Yes?
So what is Hamiltonian and Lagrangian thing? Is that a kind of energy? Or
Yes, they both are energy. And like Hamiltonian is expected to conserve kinetic plus potential.
Oh, okay.
Kinetic minus potential, it doesn't need to be
Lagrangian
conserved.
energy.
Yes, Lagrangian energy. It is very comfortable mathematical construction that helps to find correct trajectory.
Okay.
And if one performs a couple of Newton equation of, yes?
Quick question about action. Can it be negative or is there an absolute value?
Suppose we have zero kinetic energy or very large absolute value of potential energy. Then it will be negative.
So it can be a negative.
Yes. At least I'm not aware of any restrictions. So Newton's equation of motion is second derivative to trajectory equals to force over mass, right? If one performs these differential operators, so derivative of position of Lagrangian and then the derivative of Lagrangian over momentum and then once more derivative over time, then this construction will reproduce the same equation of motion as we typically get from Newton. And if you will take advanced classical mechanics and physics, highly likely you will solve equations like this as a homework. Here it's only for information. You're not going to solve it. Okay, done with list action. Part number 2. So I promised two parts. One about list action principle, and all will be connected to Bohr's atom. And second one is a little discussion about dimensionality of angular momentum. So, what is dimensionality of position? X or meters, right? What is dimensionality of momentum? It is mass, like kilograms or whatever, times it is derivative of position over time. So it is dimensions of position over time, whatever, seconds. Right? So position square over time times mass. Now, as a side note, let's recall the dimensionality of energy, like kinetic or potential. They should be the same dimension. So, what's dimension of kinetic energy? Like, mass, and then velocity squared, which means position squared over time squared. Now let's compare these two things. What's the difference between dimensionalities of angular momentum and energy? So they both have position squared in the numerator. They both have time in the denominator. Huh? Oh, square. I have forgotten square. Please find Marie. Who first found it? Rush to declare, and it will be extra points for finding my errors. So they both have mass, and the only difference is the time. So if we multiply energy by time, it will have the same dimensionality as angular momentum, right? So the stuff that defines these nodes and lobes in the Bohr orbital is energy times time. Or positions times momentum. Yeah. Oh, there are little errors here. So the Lagrangian has dimensionality of energy. And if we integrate it by time, then dimensionality of action will be energy times time. Or the same as angular momentum. So we are not making any strict mathematical proofs, but there are prompts and hints that probably those things are connected. The angular momentum that defined these lobes and nodes in Bohr model of atom, and action that should be minimal along correct trajectory are connected. So it's kind of action is being accumulated on the circular trajectories, and action divided by Planck constant defines the phase of the sines and cosines. It's a hypothesis. We do not have mathematical proof, but our hypothesis is that the action that must be minimal and that is accumulated along trajectory is entering the Bohr's atom, developing along trajectory, and defines where we will have minima and maxima. So action divided by Planck constant will be an argument of trigonometric functions of a wave in a Bohr atom. If I didn't make any mistakes. Okay? That's it. Done for today. It's too early for any homeworks or labs. There will be, after we accumulate enough knowledge, there will be office hours connected with, optional labs at Wednesday evening. You saw it in the syllabus and online. So it will be Friday from 5, same building, first floor. Alisa knows. Okay. But no lab today, no homework today, just relax and at free time think about list action.
I have a question about the actual level.
Okay.
I'm a tricolor student from SUM, and I don't know if I'll be able to get back and forth between campuses in time.
The lectures are broadcasted online.
Yeah, so is it okay?
Absolutely. There will be a link that you can connect to. Send me a reminder. I will send it to everyone. If you send me a reminder, I will do it earlier. So please, do not worry. That's completely acceptable.
Then I probably won't be here on Friday.
Yeah.
Thank you, Doctor.